Hi, welcome to our talk about pre-training federated text models for next word prediction. I'm Joel Stremmel, my co-author Arjun Singh and I are happy to be presenting to you today. We come from the University of Washington. We did this work in a graduate program there on data science in partnership with software engineers Keith and Peter from Google and our instructor, Megan Hazen. Thanks very much again for joining. I'm excited to see all the other great presentations at this conference when the time comes. With that, we'll jump right in. Our presentation is about applying pre-training approaches to the domain of federated learning. Federated learning takes the idea of optimization using an algorithm like stochastic gradient descent and applies it to decentralized distributed data entities. You can think of these as nodes in a network, or in the case of next word prediction, which is one application that Google uses for federated learning. You can think of mobile phones as containing the sensitive text message data of many different users in a network, and rather than centrally aggregating all of that text message data from those users on one server to train a model to do next word prediction, you can actually bring the model parameters to each device and then average weight updates from those individual devices during a training procedure in order to train a model across all of the nodes in this network. Transfer learning is a common idea in machine learning. You can train a model on a large data source and then apply some of the weights from that model or all of the weights from that model to do further training or fine-tuning on a different data set, often when it's harder to collect labels for that data, but you can learn some structure from that larger initial pre-training data set. This has been applied effectively within image classification. If you wanted to classify a hot dog or non-hot dog, you could do that by first pre-training on ImageNet, collect a lot of images, learn some structure of the images, and then fine-tune your classifier on a few images for the task that you're particularly interested in. In NLP, this has been done very successfully with self-supervised learning, where models will do masked language modeling or next word prediction or next sentence prediction, and learn some information about the structure of text before being applied to downstream tasks like document classification or named entity recognition. Now, our problem is to pre-train a federated model in order to potentially increase the model's performance, but also reduce the number of training rounds required in this decentralized federated training process. And we use an LSTM neural network as our model and apply a number of pre-training approaches, including central pre-training, followed by federated fine-tuning. We do this in a simulated federated environment using the TensorFlow federated framework. We also incorporate pre-trained word embeddings instead of using a randomly initialized embedding layer in our LSTM model architecture. And then we combine these two approaches. Before doing some of these experiments, we first looked at should we use two stacked LSTM layers with 128 units versus one with 256. We went with one LSTM layer based on some performance analysis on a data set of Stack Overflow posts, which I'll talk about more here. Our model architecture is applied to a data set consisting of Stack Overflow posts. I believe there are something like 130 million posts from 300,000 users in the train set. You think of these as clients in the federated context. We sample 10 of these clients per training round, and the model optimizes the objective function of sparse categorical cross entropy loss, where we try to predict the next word given some of the previous words. All of the posts are truncated to be just 20 tokens each, and we use 20,000 validation samples through the training process to figure out when our model is starting to overfit. Yeah, next slide. We use this Stack Overflow data set, which is accessible through the TensorFlow federated module using a kind of loader script. There's also a Shakespeare data set there, which is a nice federated data set because you can think of speakers in a play as clients or users and their lines as posts. And so while the data is certainly different in terms of kind of the style of English used there, it's a natural fit for federated training and also a part of TensorFlow federated. So we did the experiment there, doing some pre-training on the Shakespeare data and then fine-tuning on the Stack Overflow post data, and found that doing that pre-training actually improved the predictive ability of the fine-tuned model on the Stack Overflow data for next word prediction. However, pre-training on the same data source of Stack Overflow and then fine-tuning on that data source did not yield performance improvements in our limited experiments. And you can see model performance starts to plateau around 500 epochs. We can think of this as federated training rounds. These training rounds are very expensive, even in a simulated federated context. In the later experiment, we compared directly to the number of epochs used in another paper. So I'll share that plot as well. But the other idea that we applied in our work, besides central pre-training, is using word embeddings, where we initialize our model's embedding layer with pre-trained word embeddings. Because some of the embeddings we wanted to use are very large in size, we actually applied a dimensionality reduction algorithm here, algorithm 2 from Ronick et al. A naive approach to reducing the dimensionality of word vectors would be to use PCA. This algorithm actually applies some combination of a post-processing algorithm by Mu and Viswanath. This essentially eliminates some of the directions of variation in a word vector in order to make them more discriminative, as demonstrated in some word similarity benchmark tasks. And then Ronick et al., their work builds on this to actually do dimensionality reduction and preserve the effectiveness of these word embeddings in the downstream tasks that they tested. Won't go over this slide, but it does talk about the effect on variance explained when you do this procedure for word embedding dimensionality reduction. So we tested glove embeddings, fast text embeddings. Glove embeddings are learned based on probability of word co-occurrence in a corpus, fast text based on character level n-grams, predicting the target n-gram given the context of a word or vice versa, and GPT-2 word vectors, which are learned by training a large transformer model architecture to essentially predict the next word. And so when we applied these experiments, we found that pre-trained embeddings slightly outperform random embeddings in later training rounds, although random embeddings start to catch up eventually. However, if we can achieve the same level of accuracy or a slightly higher level of accuracy sooner in terms of number of rounds, then we're doing well. So the fact that we get better performance sooner with pre-trained embeddings is a good sign here. And you can see in this table that actually the dimensionality reduction algorithm, which uses PCA in this post-processing algorithm as shown previously, when we applied that to the GPT-2 word vectors, we did better in terms of test set accuracy on 1 million text samples from the Stack Overflow data test set, both in terms of accuracy when all tokens are included, as well as when we remove special tokens, which you wouldn't want to use to measure performance in a production use case, such as an out-of-vocab token and an end-of-sentence token. Here we see that this approach of dimensionality reduction on the GPT-2 vectors, when that is used within the embedding layer of our LSTM model, we actually outperform an LSTM model that uses random embedding. And again, we get that level of performance faster with fewer training rounds. Here you see how the performance comparisons differ for models of various sizes. We did limit our models to fairly small in size, especially if you think about using these models on mobile devices. But the number of, the weight size and the number of parameters is very critical. Now, when we combined pre-trained word embeddings and model pre-training, we did not get a positive result here. I think part of this may have to do with the difference between the data sets that we tested. And there's certainly more work to look at both pre-trained word embeddings and full model pre-training. Now, we did a direct head-to-head comparison to the training procedure used in the adaptive federated optimization paper from Google, where they do a federated learning procedure to train their model by sampling, I think, 50 clients per round instead of 10. They train for 1,500 epochs, and they measure accuracy without the out-of-vocab or end-of-sentence tokens on the last 100 validation rounds. Here, our approach outperforms their approach, which just used random embeddings. There are definitely opportunities here for future work, including using other federated data sets, federated pre-training, simulated federated pre-training with federated fine-tuning, and then federated training of a transformer-based architecture, not just an LSTM. Thanks very much. Please check out our paper and our Git repo. Very happy to be a part of the conference. Have a great day.